Now we consider Rutherford scattering cross-section. We consider Rutherford scattering, and finally we arrive at a formula for scattering cross-section. So here we are considering that a positively charged particle of charge Z e, small z e, and mass m is scattered by a heavy nucleus. Okay. The particle can be alpha particle, which is a positively charged one, and it is being scattered by a heavy nucleus. The nucleus is assumed to be at rest during the collision, and the charge on the nucleus is capital Ze. Okay, where Z is the atomic number of the nucleus. So a positively charged particle passes near a nucleus and it is being scattered. So this is what we are considering. So this is the situation here. This N, this is the nucleus, and here we have a charged particle. This is the charged particle. It approaches the nucleus. Now due to the force of repulsion between the nucleus and this charged particle, both are positively charged, it gets repelled and it moves in a path like this. And we say this particle is scattered by this nucleus. Okay. So the force, as the particle approaches the nucleus, the repulsive force acting on it is given by capital Z small z e square 4 pi epsilon 0 r square. Okay. And as it approaches, the r decreases, the distance r, this is r, the distance from the point nucleus to the charged particle. Okay, nucleus to the charged particle, that is r, and theta. So r and theta, the two coordinates, the plane polar coordinates used to describe it. Okay, this repulsive force increases and the particle changes from the straight line path to hyperbola ADB. Okay, this was coming in a straight line from here and it changes into a hyperbolic path. And phi, we know, that is the scattering angle. This is the initial direction and this is the final direction. That change is phi. Okay. So the asymptotes AO, this is asymptote AO, and this is the asymptote BO to the hyperbola, that give the direction of incident and scattered particle. Angle COB. Okay, angle COB, this angle, this is the scattering angle, and this NM, see this NM, this is the impact parameter, the perpendicular distance from the nucleus, from the center of force to the direction of motion, initial direction of motion. That perpendicular distance, that is the impact parameter, okay, which is S. And we know the equation of the conic section when a particle is moving in a central force field. The force that the force of repulsion between the particle and the nucleus that we are considering is a central force. And in the central force field, the equation of its path, that is given by L by R equal to 1 plus E cos theta. Here we are taking theta 0, the initial angle that is taken to be 0. Okay, the initial angle theta 0, that is taken to be 0. Here we know L is J square by mk. We know what is J is the angular momentum, which is a constant. And E, the eccentricity, that is given by root of 1 plus 2E j square by mk square. E is the total energy. And when the particle is far away from the nucleus, when it is coming towards the nucleus, its energy, the total energy, that will be completely kinetic. So we can say E is the initial kinetic energy of the particle, okay, the total energy. The force is given by F equal to Z E square. You know, this is the repulsive force. The charge to the two charges are small z and capital Z. This is equal to Z E square by 4 pi epsilon 0 1 by r square, which is equal to minus k by r square, and k is given by minus Z E square by 4 pi epsilon 0. L, the lattice rectum that we know, j square by mk, we substitute. For k we have now got as this. We substitute and we get minus j square 4 pi epsilon 0 capital Z small z E square m. And the eccentricity is given by this. We substitute for that k. We substitute for k and we get this expression for the eccentricity. The k is substituted. Okay. Now we know the angular momentum J, the magnitude of the angular momentum, that is given by mr square theta dot. Okay. And that is equal to mv0 s. V0 is the initial velocity, s is the impact parameter that we have already seen. So we can write mv0 as equal to v by s. Also, mv0 being momentum, we know p square by 2m. That is equal to the energy, and p equal to root 2me, so mv0 is root 2me. So one can write j by s as equal to root 2me and j equal to s root 2me. And eccentricity, we know that is given by 2e. For j we are substituting this. J is s root 2me, that we substitute, and we get E as equal to root of 1 plus 2es 4 pi epsilon 0 by small z capital Z E square whole square. And this quantity, you know, that is positive quantity. This is a positive quantity. So E will be greater than 1. E greater than 1. The eccentricity will be greater than 1 because this is a positive quantity. Also, L by R, you know, this is the equation for the conic section. Here, since E is greater than 1, what that means is the path taken by the particle, that will be it will be a hyperbola. Okay, the path of the charged particle will be a hyperbola because the eccentricity is greater than 1. And we had seen for E less than 4 in the case of planetary motion, there E is less than 1, and there we have elliptical path. Now, as the hyperbolic path is symmetric about the axis, we know the hyperbolic path, this is symmetric about this axis. Okay, hyperbola is symmetric. So here we can say phi plus 2 alpha is pi 180. Phi plus 2 alpha, that is 180. Okay. So phi equal to pi minus 2 alpha. Okay. Phi plus 2 alpha is pi. So phi will be equal to pi minus 2 alpha, and alpha equal to pi by 2 minus phi by 2. Pi by 2 minus phi by 2. Now, asymptotic direction is such that r is infinite, okay, in the asymptotic position. A and B are the asymptotic, of A and B are the asymptotes. Infinity is coming from infinity. So the R is infinity, so this L by R is 0, so this is 1 plus E cos alpha, and cos alpha we know that is equal to minus 1 by E. Cos pi by 2 minus cos pi by 2 minus phi by 2, that is minus 1 by E, because alpha we know that is pi by 2 minus phi by 2. So here we will get sin phi by 2 equal to minus 1 by E. Cosec phi by 2 equal to minus E. Cosec square phi by 2 is E square. 1 plus cot square phi by 2. Okay, 1 plus cot square phi by 2 is E square, and E square is this 1 plus 2 ES 4 pi epsilon 0 z d square whole square. Okay, so cot phi by 2, that is 2 ES 4 pi epsilon 0 over small z capital Z E square. Okay, cot phi by 2, where phi is the scattering angle, and from this one can obtain the scattering angle. Okay, one can obtain the scattering angle. Now the S, from this the impact parameter I can find, and that is equal to ZD square cot phi by 2 by 2E 4 pi epsilon 0. And differentiating with respect to phi, we will have ds d phi as equal to minus, we are differentiating with respect to phi. So cot phi by 2 becomes cosec square phi by 2 into 1 by 2. Okay, so sigma of phi, that is the scattering cross section as a function of scattering angle, we have written S by sin phi modulus of ds d phi. Okay, so this is z d square. For S we are substituting this, and the sin phi we have here, and for ds d phi we are substituting this. We have just found ds d phi. Okay, and we are writing sin phi as 2 sin phi by 2 cos phi by 2. So we substitute, and we get, and when we make these changes and multiply, we will be getting sigma phi, the scattering cross section, as a function of phi as equal to this 1 by 4 z small z capital Z E square 4 pi epsilon 0 2E whole square cosec raised to 4 phi by 2. This is a well-known expression for Rutherford scattering cross section. Okay, Rutherford scattering cross section. This is a well-known expression for the Rutherford scattering cross section. Thus, the scattering cross section is proportional to cosec raised to 4 phi by 2. Okay, and square of the charge on the particle, it's proportional. We can see ZE square, and square of the charge on the nucleus, and inversely proportional to the square of the initial kinetic energy. So the scattering cross section depends on various parameters like this, and this is the Rutherford scattering cross section formula.